welcome back to Smith Coding and Design. I am out in the shop today. I hope everyone's having a good weekend, enjoying a cold beer and a college football game. So what I wanted to do today is go over some external threading, and then I wanted to talk about some of the work holding that I'm using on my 5th axis 0 point. So we'll see some of it there on my cart, and then you'll probably find what's over there a little more interesting. So with that being said, let's walk over here and let's talk about external threading. So what I have in front of you are two sets of ring gauges. One is imperial, one is metric. I purchased these from Haas Tooling because they were on sale. And I've had a couple of jobs the last few weeks that required an external thread. And I was finding myself walking in the external threads while on the job, so while it was in the machine, and that was taking too long. I wanted to go ahead and improve my processes by making a spreadsheet that just had the pitch diameter offset and list the tooling for each of these external threads. That way, next time a job comes through that requires an external thread, it won't take me very long. I already know the tool that I need, and I'll have the correct pitch diameter offset to make those external threads. So with that being said, let's sort of go over this for a second. So how did I make each of these external threads? Well, I'm just using a single point thread mill. And I see that question asked a lot in the various Facebook groups, whether it's on the X7 group, I've seen it asked there, or if it's in the Tormont group, I've seen it asked there on how you make external threads. Well, how I'm doing it is I use a single point thread mill, and in fact, I use the same thread mill that I use to machine an internal thread as I would for an external thread. So for example, I believe this thread mill here is for a 1/2 13. So if I was making a 1/2 13 internal thread, I would use this same thread mill to make the 1/2 13 external thread, which I think is probably one of those two. So that's really all there is to it. Use a single point thread mill, or at least that's how I do it. Let me know in the comment section how you guys are doing your external thread mills. Again, this is on a vertical machining center mill, not on a lathe. Again, I use a single point thread mill, and what's beautiful about these single point thread mills is not only can I machine an imperial thread, I can machine a metric thread, internal and external. So really, your single point thread mill is, let's say, jack of all trades, where it can do many operations with one tool. So it's a little bit slower than, say, rigid tapping, but again, in my opinion, it's more versatile. So I've started loading up on various sizes of these. And again, going back to our test pieces here, all I have is what I'm calling a threaded stud. So there's no undercut on this. We'll talk about undercuts here in a second. All it has is a nice chamfer, and then, you know, the external thread that matches the various ring gauges, just so I can walk in that pitch diameter offset. So in the description below, I'm going to list the pitch diameter offset and the tool that I use to make the thread size. So if you guys want to, you know, purchase the same thread I'm using, these are from Online Carbide. They're around $30 a pop. I buy them because they seem to perform for me, and they're about half the price of what you would pay from someplace like Harvey Tool. So that's really all there is to it. Moving over here, so I just wanted to sort of discuss the case where maybe you need to make an undercut. So this is a fitting that I'm making for my coolant manifold, and you'll notice it has a nice undercut. And the reason why I wanted to talk about this is to hopefully save you guys some money, because not all key seat cutters are made the same. So to make this undercut, I'm using a key seat cutter. However, if we look at this key seat cutter, again, this is from Harvey Tool. Let me see if I can get it to focus. You'll notice there are no flutes on the bottom side. So if you try to make an undercut where the bottom of that is going to touch the floor, you are going to get an absolutely horrible surface finish. So what I learned is they also make key seat cutters that they call staggered teeth or staggered tooth. So as you can see, there are now flutes on the bottom side of that. So if you were going to machine an undercut that is going to touch a face on the bottom side, you want to make sure that you have flutes on the bottom of that, else you're going to get an absolutely horrible surface finish. So hopefully that will save you guys some money, because again, these are, I think, around $100 an end mill or a key seat cutter. And when I purchased this one without realizing that I really needed something with flutes on the bottom, I was rather disappointed. We can also walk over here. I have this accessory rack that I made and anodized. I made a few of these, and again, you know, pretty good surface finish on the bottom. There's some dust and grease in there. Ignore that. But again, that was using the key seat cutter with the staggered tooth. So hope that helps in terms of external thread milling. So now let's go ahead and get into my 0-point work holding. So again, I'm using a 0-point system. I'm one guy out here in my shop. In terms of mass production or anything like that, I can't compete with the big guys, obviously, or the big shops. So I try to be as agile as I possibly can. One way to do that is I have various fixtures that I can just pop on and off my 0-point system. So what I have right here is an ER40 collet fixture that I purchased from Silver CNC. So if I'm doing aluminum rod, this is typically what I go to. If I have something that won't fit in the ER4 collet chuck, I have a 3-jaw chuck here, again from Silver CNC. What I have here is a 90-degree fixture from 5th Axis. I don't have a 4th Axis on my X7 yet, so I can at least use one of my smaller Silver CNC self-centering vices. I can pop it on here, and then I can at least have 90-degree indexing. So that does help. For holding larger points, I have 2 orange vices. You know, obviously one has you know, the gripping jaws here. That way I can hold only 60 thousandths on the bottom of my stock. And then over here, you see I try to engrave these. That way I remember the step size, etc. So that would be my soft jaw. So really use that for non-marring purposes. So I will machine op 1, flip it over, machine op 2. That's how I go about that. Now what you guys will probably find more interesting is what I have over here. So for machining thin parts, or really I mainly use this for machining sheets of plastic like acrylic. This is a Pearson vacuum chuck. I believe this is the 13x9. And what a lot of people don't realize, and I didn't either, is that the Pearson vacuum chuck will fit on your 0-point. So if you have the standard 96mm spacing, again, this is the, I believe, the 9x13 vacuum chuck, it will fit on your 0-point. You can see the 4 pull studs, and that's from the factory, guys. I did not add those. So whatever you buy straight from Pearson, all you have to do is add the pull studs and you're good to go. One thing I will mention, and we'll go back to the machine, you'll notice that I am only using the outside pull studs. So if we go back over here to the X7, you'll see this fixture is using the internal, the center 4 pull studs, and the external 4 pull studs here on the outside are not being used. Now what you need to do when you're using only the outside is you need to use this, which is what's called a dummy pull stud. You put this in the center, and that way when you go ahead and torque down your 0-point system, it distributes the forces evenly and you don't break the pull studs on the outside there, right? If you only had 4 pull studs and you torqued everything down, you could be putting more force than what the pull studs are rated for, and you could break them in the 0-point. So we don't want to do that. Another cool fixture I have here, let me set this back down, hopefully I don't damage that, is I have a Saunders fixture plate. So you'll see here, this is genuine. This is from Saunders Machine Work. All I did was send them an email, and I had this made, and it works the same way that the Pearson does, is you have pull studs here on the outside. So I know a lot of you guys come from a Tormach or another machine, you're using the mod vices, and you quickly realize that on the X7, I think there's like a 3 or 4 inch gap from the spindle nose to the bottom of your table. So you can't use your mod vices because you can't reach. Well, to get around that, all that I'm doing is I'm placing this fixture inside of my 0 point, and then I can use my mod vices on this and I have plenty of reach. So the goal is, if I have large plate work that won't fit on my standard vices, I would put this bad boy in my 0 point, and then I could use the mod vices to hold those large plates. Or I might see if I can get 2 or 3 mod vices on here that are in the dual configuration, so that way, you know, I could hold 4 or maybe 6 pieces of material, and then I could use this as a mini pallet that would just go onto my rock lock. I could also bolt the blank pallets from Saunders Machine Works on top of here and use it as a mini pallet system as well. So that's really it, guys, in terms of the work holding I'm using right now on my 0 point system, and that's it for external threading. What we'll probably do now is jump in the Fusion 360, and then I will sort of go over, I wouldn't call it a tutorial, but we'll just sort of breeze over some of the single point thread mills and then a little bit of the cam that I use to make these test pieces. Again, it will be more for beginners, so it might not be as interesting to you experienced vets out there. Leave in the comments if you have any suggestions, or if you are machining the external threads in a different way and you would like to get that information out to the masses. Please comment, and please watch the following section. Thanks for tuning in.
Alright, so here we are in Fusion 360. You'll notice here I have an Excel spreadsheet up. So this lists the thread size, the pitch diameter offset, and what I will add is another column that lists the tool part number that I use to go ahead and machine all these threads. So I'll go ahead and provide this table in the description in case you guys want to pick up the same thread mill. You can use those to machine these external threads. And you'll notice here I have a series of metric and imperial threads. Again, those correspond to the ring gauge set which I purchased from Haas Tooling. So what I'm going to go ahead and do now is we'll go ahead and close this, and then we will jump into Fusion 360. So in terms of setup, it's going to be pretty straightforward. In fact, this whole project is going to be pretty straightforward. So we'll kind of breeze through everything. I don't want to waste your time. Just want to give you the information as quickly as I can here. So for the setup, what I have is just my 5th axis rock lock base. On top of that, I have an ER40 collet chuck that is from Silver CNC, and inside of the collet chuck I'm using 3/4 aluminum rod. So I'm going to go ahead and make the stock invisible. We'll zoom in here to the model. I'm calling this a threaded stud, so I made a series of these. What I have open here is just the 1/4-20 and the M6 version. So all this is a cylinder that I extruded 1/2 inch, gave a nice chamfer, and then went ahead and made the side of it threaded. And the most important part here, if I press I, is we need to make the cylinder equivalent to the major diameter of the thread we plan to machine. So in this case, we're using a 1/4-20 shown up here. So our diameter you see here is 1/4 inch. So if I go over to the metric version, this is M6. We'll go ahead and examine the diameter here. You'll notice it's 6 millimeters. Again, just making sure that our threaded stud diameter is the same as the major diameter of the thread that we want to machine. And then of course the thread we put on the side of the cylinder here, or the side of our model, we want to make sure that is equivalent to the thread we plan to machine. So going back to our 1/4-20 example, we will go ahead and jump into the manufacturing tab. We'll zoom out here, and then we'll jump into my tool library. And so what I want to cover here is the single point thread mills. So I'm purchasing all of my thread mills through Online Carbide just because they are relatively cheap and they seem to perform well for me. So they're about $30 a thread mill, compared to a place like Harvey Tool you might pay $60 to $100 a thread mill. So again, I like to advocate for single point thread mills. Why? Because you can machine a variety of threads with a single tool. So for example, let's just pick tool 10 here. If I wanted to machine a 440 thread, I would choose tool 10. If I wanted to machine an M3 thread, I would also choose tool 10. So if you notice my naming convention, I have the imperial and sort of the metric equivalent that I would use this thread mill for. And so it's going to be the same thing for internal as well as external. So if I'm machining an internal M3 thread, so I'm machining inside of a whole M3, what I would do is I would choose this thread mill. If I was doing an external M3 thread, I would choose the same thread mill. So we're doing external, internal, and we're doing imperial and metric threads all with one single point thread mill. So that's why I like single point thread mills. Again, you can perform a variety of tasks. So especially if you're like me, a one-man shop in your garage, thread mills are expensive, rigid taps are expensive, etc. It's nice to have one tool that can sort of take the job of multiple tools. I don't need two form taps. I can just use one single point thread mill, although it is slower than a form tap. So if you're doing something more production wise, then you would use a form tap. So there's always pros and cons. But anyway, that's why I advocate for single point thread mills. And again, really what I wanted to point out here is we're using the same single point thread mill that I would use to do an internal M3 thread as I would do an external M3 thread. So it's really that simple. Again, I will list the tools that I used in the description in case you want to pick them up. You have a good starting point. So moving on into the cam. Again, this is very easy, very straightforward. I'm not going to go into it in detail because of how easy it is. So all I'm going to do is a face where I'm taking off 50 thousandths from the top of the material. I'm then going to do an adaptive clearing. Here we're just removing most of the material around the walls of our threaded stud. We're going to do a 2D contour where we go ahead and finish our threaded stud. So after we do our 2D contour, we would be to that 1/4 of an inch major diameter. From there, we're doing a chamfer to give a nice starting point for our stud to insert either into a nut or into our ring gauge. And now what we'll do is we'll go ahead and get into the threading tool path. So it's pretty simple. How am I going to make the external thread? The same way I would if I was making an internal thread. The difference here is instead of threading inside of a hole, I'm going to go to thread. We'll go ahead and pick our 1/4-20 single point thread mill. I would also use this for M6 as an example. So we're going to go ahead and select that. And again, as I mentioned, it's the same as if I was making an internal 1/4-20 thread. All I'm doing here is selecting the outside of our threaded stud instead of the inside of a hole. That's really the only difference. If we go to our heights tab, one thing you could do, you'll notice that your single point thread mills are typically necked to a particular distance. You want to make sure that you don't thread past that distance. So what you could do here is you could do whole top. So we'll make our top and bottom height the same, and then we'll just come down. Let's just say 300 thousandths as an example. That way we could match the reach of our tool. Moving into passes, here's where it gets slightly more interesting. So what I did is I used the ideal case of the major diameter minus the minor diameter to start my pitch diameter offset. So again, your thread pitch is 1 threads per inch. So this is correct, but just in case you're following along and you're a beginner, for a 1/4-20 thread, it's 20 threads per inch. So I'm going to do 1 divided by 20 here. That gives us our pitch. And then for our pitch diameter offset, again, I'm going to use the major diameter minus the minor diameter. How did I find that information? So you can Google it, or what I like to carry around with me just around the shop is I have here, it's called the Engineer's Black Book, and inside it's a good resource for your drill and tap sizes, your major and minor diameters, etc. So I'm going to enter that there, and then from there I literally just walked into thread. So I would increase my pitch diameter offset from 2 somewhere between 2 and 4 thou until it fit nicely in the ring gauge. So I just walked it in once, and then it's done. You keep it in your spreadsheet, and the next time you have a job that comes along down the road, you don't need to second guess yourself, or you don't need to walk it in on the fly. You have that information there for that particular tool. So all I'm going to do now is what I normally do is I go multiple passes. We're just going to go 10 thou per pass. And then I know this is obviously adding cycle time, but I'm also going to do repeat passes just so if there's any chips or anything. Really, it's more of an issue when you're threading in a hole. This will do a spring pass and help clear any of that out. So that's it, guys. That's how we go ahead and we make our external threads. I'm just going to go ahead and hide the model for a second. That way we can see it. We could simulate it if we want. Again, it is very simple. Normally what you'll see, if this was a real product or something like that, or a real job, normally there would be an undercut here that you would use a key seat cutter, and you would come around and make that undercut just to make those threads pop out and look nice and beautiful. So that's it, guys. If you have a different method, there's also the NYCNC spreadsheet you can use that can give you some starting point numbers. It's a good resource. I use it a lot for internal threads. So again, if you have any comments, any suggestions, or if you would do it differently, maybe you don't like using a single point thread mill and you have another tool that you would like to suggest to the masses, please go ahead and leave a comment below, and I'll catch you guys in the next video. Thanks for tuning in.